Thermoregulation is a process that allows your body to maintain a certain core internal temperature. All thermoregulation mechanisms are designed to maintain or return your body to homeostasis. Thermoregulation is a necessary process in order for animals to survive, especially in extreme weather conditions. Animals are divided into two groups based on how they utilize thermoregulation. Endotherms use metabolic heat to maintain a stable internal temperature, usually one different from their environment. These organisms are warm-blooded. A few examples are birds, cows, bears, cats, and dogs. And yes, that is my dog pictured. On the other hand, ectotherms take on the temperature of the environment. These organisms do not use metabolic heat and are considered cold-blooded organisms. A few examples include snakes, lizards, and most other reptiles. Both groups of organisms have specific adaptations that help them maintain a specific, healthy body temperature. How do these animals do this? They have ways of increasing metabolic heat production, otherwise known as thermogenesis, in response to cold environments. One way they do this is through muscle contraction. This is commonly seen as shivering. Here, muscle activity is increased in order to increase the production of heat to warm the organism, like how you can rub your hands together to make them warm. Another way animals do this is by genetically having brown fat. Brown fat contains many mitochondria with unique proteins that allow them to release energy from fuel molecules directly as heat, instead of channeling it into ATP. This is very common in animals that hibernate. Animals can also develop body structures and physiological responses that control how much heat they share with their environment. There are circulatory mechanisms that can control the flow of blood through the skin in order to regulate the rate of heat loss or gain from the surrounding environment. The two categories of this are vasoconstriction and vasodilation. Vasoconstriction is a way for animals to retain heat by shrinking the diameter of the blood vessels that supply blood flow to the skin. This is important because as blood flows from the core to the skin, the temperature generally decreases. Secondly, vasodilation dilates blood vessels to increase blood flow to the skin in order to release heat. These mechanisms are prevalent in mammals with a lot of fur, but have bare areas of skin exposed with abundance of blood vessels. For example, jackrabbits with large ears have many blood vessels in order to allow heat loss to adapt to their harsh desert environments. Lastly, in countercurrent heat exchange, heat from warm blood vessels is transferred into the cold blood vessels, ultimately heating the organism. The warm blood passes its heat through conduction. Another way to reduce the loss of heat is through insulation, which may be the most obvious of them all. Some animals have layers of feathers, fur, or fat to trap a layer of air next to the skin in order to reduce heat loss. Marine mammals that live in cold waters have a thick layer of blubber, which is a form of fat, in order to properly insulate their bodies. A few organisms that utilize insulation are pictured. The last mechanism to control heat loss and gain are evaporative mechanisms. Evaporation acts as a cooling system for the organism because it removes heat by turning liquid water into vapor. Animals want to trigger evaporation to release heat, so they initiate the process through evaporation mechanisms, like sweating and panting. In order to sweat, glands in the skin release liquid water, which is then evaporated into the air, therefore releasing heat. On the other hand, panting is done by rapid, shallow, open mouth breathing. This act increases the evaporation of water by the mouth surface. Mammals and birds participate in this mechanism. Shown here is a mathematical formula used to determine the rate of heat transfer through a layer. Also listed is what each variable in the formula stands for. It can be used for all sorts of conditions, like the ears of a rabbit or even the skin of a human. Here is a mathematical example of how you can use this formula in real-life situations. We want to know what the rate of heat transfer is through a polar bear's blubber from a temperature of 34 degrees Celsius to 0 degrees Celsius. An average male polar bear is about 4.4 feet tall and about 990 pounds. We know the length of the blubber is about 4.5 inches thick, which is 0.11 meters. We also know the surface area of a bear is 5.35 meters squared. Additionally, the thermal conductivity of blubber is 0.25. We can plug all these values into the previous equation and we get a rate of heat transfer of 427.32 joules per second. Listed here are a few works that helped me make this great presentation.